Hello everyone, welcome back to CS Classroom. In today's video, we will study one of the most important topics in compiler design, machine independent optimizations. These optimizations improve program performance without depending on any particular processor architecture. More importantly, many GATE, university and interview questions are asked from these optimization techniques. So let us begin. Suppose two students solve the same mathematics problem. Student A performs 20 calculations. Student B performs only 10 calculations. Both get the same answer. Whose method is better? Obviously student B. Compiler optimization follows exactly the same principle. Produce the same output with less work. Optimization means replacing inefficient code with another equivalent version that executes faster or occupies less memory. One important rule must always be satisfied, that is, the meaning of the program should never change. Okay, నేను ఏ ఇంటెన్షన్తో ప్రోగ్రామ్ రాశానో, ఏ ఎయిమ్తో నేను ప్రోగ్రామ్ రాశానో, అండ్ నాకు ఏ అవుట్పుట్ రావాలని నేను ప్రోగ్రామ్ రాశానో, నాకు అదే రావాలి, అదే యాక్యురసీ ఉండాలి, అదే కరెక్ట్నెస్ ఉండాలి. మీనింగ్ ఆఫ్ ది ప్రోగ్రామ్ మారిపోకూడదు. నేను ఏదైతే రాశానో ప్రోగ్రామ్ నాకు అదే ఆన్సర్ రావాలి. ఓకే, దాట్ ఈస్ ద ఇంపార్టెంట్ రూల్ for optimization, any optimization. So most optimizations arise because programs contain repeated computations, unused values, constant expressions, or computations repeatedly performed inside loops. So compiler identifies such situations and improves them. Now let us discuss the actual optimization techniques one by one. Let us begin with global common subexpression elimination. Suppose an expression was already computed earlier. If the variables involved have not changed, there is no need to compute it again. Compiler simply reuses the previously computed value. Okay. Suppose మా పాప ఒక క్వశ్చన్ అడిగింది అనుకోండి నన్ను. ఓకే, 13 into 25 ఎంత మమ్మీ అని అడిగింది. సరే, నేను క్యాలిక్యులేట్ చేసి చెప్పాను. ఓకే, వెంటనే మా బాబు వచ్చి సేమ్ అదే క్వశ్చన్ అడిగాడు, 13 into 25. నేను మళ్ళీ క్యాలిక్యులేట్ చేసి చెప్పాను కదా, జస్ట్ ఇప్పుడే ఆన్సర్ మా పాపకి చెప్పాను. సో సేమ్ ఆన్సర్, ద సేమ్ కంప్యూటెడ్ వాల్యూ, ఐ యూజ్ ఇట్ అగైన్. నేను మళ్ళీ అదే యూజ్ చేసుకుంటాను. ఓకేనా? సో ఫర్ ఎగ్జాంపుల్, కన్సిడర్ దిస్ ఎగ్జాంపుల్ which is being shown on the screen. The compiler computed 4 into I and stored the result in T7. So later it encounters exactly the same computation. Has I changed? No. Then why compute it again? Reuse the old result. Okay. So instead of recomputing the expression, compiler simply reuses the earlier value. This reduces instructions and improves execution speed. A copy statement simply copies one variable into another. Compiler tries to eliminate unnecessary copies. Here, x is merely a copy of T3. Instead of using x later, we can directly use T3. This optimization is called copy propagation. Notice that the assignment to x may now become unnecessary. So this creates opportunities for another optimization called dead code elimination. Dead code elimination removes computations whose results are never used. Suppose a compiler encounters this statement, x is equal to 10. If x is never used later in the program, then this assignment serves no purpose. So the compiler removes the statement completely. Why waste the time computing a value that nobody uses? Okay. Now let us discuss constant folding. Compiler evaluates constant expressions during compilation itself. Instead of asking the processor to add 3 and 4, see 3 plus 4, 3 and 4 every time the program executes, Compiler performs the calculation once during the compilation. So program execute చేసే ప్రతిసారి 3 plus 4 3 plus 4 3 plus 4 మళ్ళీ కంప్యూట్ చేయాల్సిన అవసరం లేదు. కంపైలర్కి కంప్యూటేషన్ టైంలోనే ఆ ఆన్సర్ ఏంటి అనేది దానికి తెలుసు. సో ఇట్ కెన్ జస్ట్ ఫోల్డ్ ది ఆన్సర్. ఈ ఆన్సర్ని జస్ట్ ఫోల్డ్ చేసేయచ్చు. దీన్ని కాన్స్టెంట్ 3 plus 4ని 7తో రీప్లేస్ చేయొచ్చు. ఓకే, దట్ ఈస్ కాల్డ్ as కాన్స్టెంట్ ఫోల్డింగ్. So compiler performs this calculation during the compilation time itself. Okay, loops execute many times. అది మనకు అందరికీ తెలుసు. Therefore, computations inside loops are very expensive. If a computation does not change during the loop execution, it can be moved outside the loop, right? Okay, దాని loop లోపల పెట్టడం ఎందుకు? Time waste, resources waste. For example, if you see while I less than or equal to limit minus 2. Observe the expression limit minus 2. Does limit change inside the loop? No. Then the same calculation is repeated unnecessarily. ఎందుకు అన్నిసార్లు ఆ లూప్ ఎన్నిసార్లు రిపీట్ అయితే అన్నిసార్లు లిమిట్ మైనస్ 2ని మనం క్యాలిక్యులేట్ చేస్తూ ఉండాలి. ఓకే, సో the expression is computed if you keep that expression outside the loop. See the optimized version. If you put it just before the loop, it is computed only once before entering the loop. So this optimization is called code motion. Just we are moving the code outside the loop, we are moving it to out of the loop. Move చేస్తున్నాం. That is why it is called as code motion. Okay. Next, we have induction variables. An induction variable changes by a constant amount during every iteration. So if you look at this loop for I is equal to 0, I less than n, I plus plus, I అనేది every iteration కి +1 కాన్స్టెంట్, అంటే ఒక చిన్న ఒక కాన్స్టెంట్ వాల్యూ చేంజ్ అవుతూ ఉంటుంది. I plus 1 కాన్స్టెంట్ అమౌంట్ చేంజ్ అవుతూ ఉంటుంది. ఓకేనా? సో here I is called as an induction variable. Okay, I'll come to the induction point again, induction variable point again. Strength reduction. Strength reduction means replacing expensive computations with cheaper ones. Okay, see if you look at this example, j decreases by 1 in every iteration. J is equal to j minus 1. Then 4 times j also changes predictably. Okay, see here, T4 is equal to 4 into j. Then why can't we optimize the code as instead of performing multiplication during every iteration, compiler simply subtracts 4. So instead of these two lines, it simply writes it as T4 is equal to T4 minus 4. Subtraction is much cheaper than multiplication. So if you substitute a costly operation with a cheaper operation, then that is called as strength reduction. You are reducing its strength. కాస్ట్లీగా ఉన్నదాన్ని, బాగా కష్టంగా ఉన్నదాన్ని ఈజీ చేస్తున్నారనమాట. సో దట్ ఈస్ నోన్ యాజ్ స్ట్రెంగ్త్ రిడక్షన్. ఓకే, సో ఇండక్షన్ వేరియబుల్, ఇందాక చెప్పాను నేను ఇండక్షన్ వేరియబుల్ అంటే ఏంటి. లూప్లో ఇన్ ఎనీ లూప్ విత్ అ స్మాల్ కాన్స్టెంట్ అమౌంట్ ఒక వేరియబుల్ ఏదైనా చేంజ్ అవుతూ ఉంటే దట్ వేరియబుల్ ఈజ్ కాల్డ్ యాజ్ ఇండక్షన్ వేరియబుల్. ఓకే, సో సమ్టైమ్స్ two induction variables always maintain a fixed relationship. Two induction variables. In such cases, one variable can be eliminated entirely. One variable can be eliminated. So by eliminating redundant induction variables, loops become simpler and faster. Okay, so benefits: less computation, fewer variables, and faster loops. So today we studied the most important machine independent optimization techniques. Remember the overall goal: do not repeat computations unnecessarily, do not compute values that are never used, do not perform expensive operations when cheaper alternatives exist, right? Okay, so these simple ideas form the foundation of modern compiler optimization. So before we end today's class, notice something interesting. Most of these optimizations are based on common sense. If a value is already available, reuse it. If a value is never used, remove it. If a calculation never changes, move it outside the loop. Why to repeat it? Why to iterate it? And if a cheaper operation can produce the same result, use it. A good compiler follows exactly these principles. In our next video, we will continue with the data flow analysis. Thank you for watching. This is Padma from Mana CS Classroom. See you in the next video. If you liked the video, please subscribe to Mana CS Classroom channel. Thank you.